Hey, we have another integral here today. We've got the integral from 0 to 1 of x cubed over 1 plus x dx. Okay, pretty straightforward problem, but I just kind of like the methods I had for this one. I have a couple methods that I like for this one. I have a straightforward method and then a less straightforward method. So to get started, let's just kind of do the more obvious thing, or the straightforward way. I just want to add a plus 1 on here, try to set up some cancellation with the algebra, but I don't want to change it, so let's subtract 1. And then let's separate this into two integrals, but for the first one, I can use the sum of two cubes formula because we have the sum of two cubes in the numerator. So when I do that, let's just, to save a step, let's do the factoring all in one step. So x cubed plus 1, I can write this as x plus 1 times x squared minus x plus 1, just using the formula on that. Then of course we have our 1 plus x in the denominator, and the second part's just going to be this minus 1. So I'll bring the minus out front, and we'll write it as just dx over 1 plus x. This one, of course, is going to be easy. This one we have cancellation. I can just cancel this with this. So now we have power rule here, easy integral. Let's go ahead and integrate. So this is going to become with power rule x cubed over 3 minus x squared over 2 plus x. We'll evaluate these all together. Then here, minus natural log absolute value, I'm going to drop it because our x values are always positive, so we've got no problem dropping absolute value. We'll do parentheses and evaluate from 0 to 1. Then just notice at 0, everything gets zeroed out. All this stuff is 0. This will become natural log of 1, so let's not worry about that. Plug in 1, we get 1/3 minus a half plus 1. Here we have a minus natural log of 2. Let's just get a common denominator on everything. So I can write this as 2/6 minus 3/6, and then this will be a plus 6/6. Adding up all this stuff, for the solution of this, we just get 5/6 minus ln 2. Okay, now on to method number 2. I think I like this way better, even though it's probably slower, but that never really bothered me. So for this 1 plus x, I can rewrite it a little bit. I can rewrite it as 1 minus x. The reason I do it this way, I just want to notice, kind of create a 1 there, and we notice the similarity to our geometric series formula. If we have just write 1 over 1 minus x, this is going to be the same thing as the sum from 0 to infinity of x to the n, assuming, important assumption, that we need the absolute value of x to be less than 1. So here, with what we have, not worried about the x cubed right now, we're just focused on this part right here. Our input into this formula is going to be the minus x. So it's like plug that in here and then plug it in here. So before we do this, we need this check on it. So what we need to happen is we need absolute value of minus x to be less than 1. Well, noticing the bounds, our x values are all between 0 and 1. Don't worry about the endpoints on an integral. It's like, think of that like a limit. So if all these values are between 0 and 1, minus sign inside the absolute value, don't worry about that. This is going to work. We're going to be less than 1. So we can go ahead and use this formula. Now doing this, let's just write it out for the case we have, which is going to be we're inputting minus x here. So what's going to happen for our sum, instead of plugging in x there, we're going to have minus x. So we have this as minus x to the n. But then actually let's split out this minus sign. So what I can do for the minus sign, just distributing in the exponent, we can write it as minus 1 to the n times x to the n. And so let's just take what we found right here and plug it back into our integral. So now our integral is, we're going from 0 to 1, x cubed times this thing. And then at this point we notice we've got the same base here, x and x. We can just multiply this back in, combine it with this x right here, and this is going to become x to the n plus 3 over here. And then from here, let's just swap the order of the integration with the series. So we'll swap this with this. We're okay to do it. We've got absolute convergence with the geometric series formula. And then one last thing I can do before I integrate, notice this again, this is just a constant with respect to x. We can bring this outside of the integral, bring it out right here. But now just notice that what we have right here, this is going to be just an easy integral. We've got base of x, n plus 3 is just a constant, so we can just use power rule on this to integrate. So we'll go ahead with that, bring over our series stuff that we still have in front. Integral here of this is going to become n plus 3 plus 1 now. So we end up with n plus 4 in the exponent over n plus 4, and we just need to evaluate from 0 to 1. But when you plug 0 in, when you plug 0 in, you just get 0. You plug 1 in, 1 to the n plus 4 is just 1. So everything in the numerator is just going to break down to 1. Let me rewrite this. Putting this together, this whole thing right here is just going to become 1 over n plus 4. Let's combine it like this and put this n plus 4 in the numerator here. But what we have right here is really interesting because you may recognize this. This is really similar to our alternating harmonic series. There's a couple problems on it. For the alternating harmonic series, we've got like n plus 1 or n minus 1 on the exponent. And this should just be an n right here. Well, for this, I can do an index change real easy. What you can do is, if you just subtract, in this case 4 to clean it up, we can subtract 4 on the end. So I can just do it like this, subtract 4 here. But so that I'm not changing it, I need to do the same thing on the index. So we'll change this to a 4 here. Quick rewrite, what's going to happen? This is just a 0 right here. So what we end up with is we just have an n in the numerator. For this n minus 4, there's no need to add even numbers on the exponent of minus 1 because it's going to be the same. Like n is going to be the same thing as n plus 2, n minus 2, n minus 4. So I can just put this back and write it as minus 1 to the n. But now here we're starting our series at 4. And so now we're almost done, but what I want to do is let's take this and compare this to our alternating harmonic series just to see if we can get this in terms of a numeric solution. I mean, of course, this is definitely not this. So what can we do to get this thing to look more like this? Okay, so we found this series over here to the left that we want to get a value for. And what I want to use for this is the alternating harmonic series, which we have over here to the right. I have this value. This is a known value for this is natural log of 2. We've derived this a couple times in other videos. So I'm not going to derive this again, but I can provide a link to the other video where we found this value. And so the main problem we have comparing this to this is just the index. Here we're starting at 1, here we're starting at 4. What I can do with this is just strip out a few terms, just kind of plugging in values. So like for the n equals 1 value, we plug in 1 here. We get 2 in the exponent. So this first term is just going to be a 1. The second term, you plug in a 2. Now we end up with a minus sign in front, and we have 1/2. The third term, when n equals 3, this becomes a plus 1 over 3. And then for the fourth term, we're just going to leave it. We're just going to update our index. We'll update our bound here to 4, going from 4 to infinity of this thing. And from here to here, we haven't changed anything. We just stripped out a few terms, so this is still just equal to natural log of 2. Then this right here is almost this. The only problem now is just this exponent. Well, for minus 1 to the n plus 1, we can split this out, exponent properties. Minus 1 to the n plus 1 is the same thing as minus 1 n times minus 1. But then now let's just take this minus 1 out front. I can use to change the sign here, make this a negative. And now at this point we notice that what we have right here, this is exactly the thing we want to find. We just have to kind of rearrange this to solve for it. Let's kind of put a label. We'll call this here S. I'll call this S. So what I can do is let's add an S on both sides, add an S here, but then let's subtract off the ln2, subtract off the ln2. Let me just clean up to show what I'm doing. So for our S, our goal, we end up with all this stuff over here, 1 over 1 minus 1/2 plus a third, and then we have this minus ln2 over here because this canceled on the right side. So we've isolated our S. But then we just need to simplify it, common denominator like we did before. This becomes 6 over 6 minus 3 over 6 plus 2 over 6 minus ln2. Adding this up, same thing we did before. For my final solution of this, we have just 5 over 6 minus ln of 2. Okay, there you go. Pretty basic problem, 2 interesting methods. Thanks everyone for watching. Have a good day.